Okay, so we are now at the top of page 4, and we're going to continue prepping this first hypothesis test. And again, our question of interest is, are we doing better or worse than random chance in this particular game? So we're going to set up two competing hypotheses. And the first hypothesis is what's called the null hypothesis. And so there's a definition here. In this particular example, our null hypothesis, the definition says that it's usually represented by equality. And so in this example, our null hypothesis is that the proportion is equal to 0.25. So what this means in words is that the proportion of all matches so I'm going to reword this, apologies. So in all matches we play, the proportion of times we win is 0.25. The competing hypothesis with this is what's called the alternative hypothesis. And so it's defined as usually being represented by a range of values. And so in this particular context, we're going to write HA is usually our notation for the alternative. HO is usually the notation for the null hypothesis. So the alternative is that the proportion is not equal to 0.25. So I'm going to use these quotes again to just mean that I'm mirroring the same words as above because the wording is almost identical, except at the very end, I'm going to say is not 0.25. So it could be higher, could be lower. Both of those settings are covered by this alternative hypothesis. There's a final definition here called the null value. And so this is the value that we are comparing our parameter to up in this null hypothesis. It has some special notation, which is why we have this little final definition. And its notation is P naught or P0. So that's just whatever this number is, comes from context of the problem. We have specific notation for that. Okay, so we've set up a couple of competing hypotheses, and much of what the rest of this initial example will be about is how we're evaluating these two competing hypotheses based on the data, so based on the 50 matches that we collected. Ultimately, we're going to end up with a value that's called the p-value. And so it has kind of a wordy, complex definition. So it's the probability of observing data that is at least as favorable to the alternative hypothesis as what we actually observed. So the probability of observing data that's at least as favorable to the alternative hypothesis as the data that we actually observed or as the data that we actually got. And if that wasn't enough, there's a little bit more if the null hypothesis is true. Okay, so that's a very complicated definition. For now, we're just going to kind of ignore it a little bit, but we're going to make the important note that this is some probability that's computed, and it's a probability computed under the assumption that the null hypothesis is true. So that part will be really important with what we decide to do on the following page. But before we move on, there's this little bullet point that'll let us summarize some of the notation we've used so far, just so we've got a good grasp on it. So by now we've been using this P with a little hat to mean our sample proportion that we're getting from data that we've collected. We've been using this P without the hat as the population proportion. And unless we have a census, this value is almost always unknown. So we don't know what this true proportion is. And now we have the p with the little 0, and so that is our null value. Okay, so again, what we want to do is evaluate these competing hypotheses with data that we've collected. And so if you look back on, let's see, back on, I think it's the top of page 3, we've won 16 of the 50 matches in the data that we collected. So we'll write down our sample proportion in this spot, so 16 out of 50. And that sample proportion turns out to be 0.32. So our big picture question is this sample proportion from the data that we've collected, is that different enough from 0.25 to conclude that we are doing better than random chance? Or is it close enough to 0.25 that we can't really conclude that we're doing better than random chance, and maybe we just happen to get a slightly higher proportion because of natural sampling variability? That's the big picture question that we'll answer. And so I'll pause this video here and we'll get into the remaining steps in the next video.